Under the chapter solid state, we are going to discuss some aspects about solid state. That is, while you are crystallizing a solid, even though proper care is taken, but the particles in the matter or crystal possible to deviate from their positions. Even though stricter invigilation is going on in the examination, one or two students may be deviated towards writing examination and they will look into other people. Like that, this is also, even though proper care is taken in the crystals, the particles may be deviated from their positions. That leads to imperfection of solids, that is known as crystal defects. So, present topic is the objective of the lesson or this video is crystal defects. Yes, crystalline solids have two types of arrangement of the particles: long range order and short range order. And even though proper care is taken, they will be deviated from their positions, and that leads to imperfection in solids known as crystal defects. Nothing but imperfection in crystalline solids. Right. In what way the particles are deviated? Suppose if we take the arrangement of the particles like this, yes, the particles along a point deviated. The particles are deviated along a point, that is known as point defects. Dislocation along a point, what you are observing. Suppose the particles are missed along a row. Along a row, the particles are missed. Observe, along a row the particles are missed, and that is known as line defects. So, imperfection observed along missing of the particles along row. Right. That is a very little information regarding our syllabus. This is the area we are going to discuss in detail about point defects, which are observed as a dislocation along a point, or imperfection along a point is observed as point defects. Point defects are further classified based on the situation, that is, take a overall view. Point defects classified into various types. Yes. That is, point defects are stoichiometric and non-stoichiometric defects. So these are without changing the formula, that is known as stoichiometric defects. If we add a foreign material to this solid, this is a solid, foreign material is a little bit added, that is known as impurity defect. And due to dislocation distribution of the particles or missing of the particles, and the formula of the compound is changed. Here the formula of the compound not changes, stoichiometric. Here the formula is changed, that is known as non-stoichiometric. Non-stoichiometric defects. This is a minor idea about defects, even though proper care is taken. And crystals have which type of forces? Crystalline solids. Crystalline solids have two types of arrangement of particles. One is long range and short range order. Order of arrangement of particles observed. Arrangement of particles. That is noticed, and due to this, even the proper care is taken, the particles are missed, leads to imperfection solids, which are known as crystalline defects, which are known as defects in crystals. Under point defects, first of all, we are going to discuss about stoichiometric defects due to dislocation or missing of the particles. The formula of the compound not changed. Such defects are called stoichiometric defects, also known as intrinsic defects. Intrinsic or thermodynamic defects. Thermodynamic defects. Yes, this is observed in two types of solids. This is observed in covalent solids and also observed in ionic solids. Right. Observed in covalent solids, what is noticed? Very simple. With the help of diagram, you can easily catch that one. The first one is, these are the arrangement of particles. Yes, what you are watching. Even though proper care is taken, the particles are missed around a point, completely missed from that one. The student left the classroom, so that seat is vacant like that. So here, this is missed, vacancy, and this is missed, vacancy, this defect is. So here what happened? Some particles are missed from their lattice points. Some particles or atoms missed from their lattice point. And what is resulted? A gap is resulted. Missed and vacancy is created. Vacancy is resulted. Due to this, what happened to the density? Formula is not changed, that is stoichiometric defect, and density is decreased. Why? Because out of 12 particles, 10 particles are now available, 2 particles are completely missing from the positions. So density decreased. Density decreased. What happened to, yes, how is it resulted? If you sometimes heat the crystal, this type of defect is noticed, and this defect is known as, this defect is now known as vacancy defect. Vacancy is created and it is known as vacancy defect. This vacancy defect is observed in covalent solids. In covalent solids, vacancy defect is observed. How is it? Due to missing of particles from their lattice points. This is due to this, density is decreased, and sometimes if you heat the crystal, this type of defect is resulted. It is resulted due to heating. Sometimes it is resulted due to heating the crystal. I hope you followed this one as covalent solids. In covalent solids, vacancy defect. Now observe this diagram, dear students. Yes, this what you are showing is, what you are observing is gap. The gap among the particles in the crystal is known as interstitial voids. This is interstitial void. I would like to mark with a color if you are interested. Yes, this is a gap. This is a gap for watching purpose. This is a gap, watching purpose. Right. The particle is dislocated from its position and occupy the void. The particle. So, if the particle is here removed and it is occupying here, this particle is removed here and here it is occupied. So, this type of defect is known as dislocation and it is known as interstitial defect. B. It is interstitial defect. These two are observed in here. More concentration of particles are located or gathered and density is increased in this case. Now observe the information, dear students. What is this information? Dislocation of particle from its side position to occupy void, nothing but interstitial space. Interstitial space. Due to this, what happened to density? Yes, density is increased. Density is increased. These are the points. Yes. These two types of defects observed in covalent solids. The same information also observed in ionic solids. That will be discussed very soon. Get ready. Now, time to discuss the defects, point defects under in ionic solids. Take one ionic solid, that is NaCl, Na plus, Cl minus, alternatively arranged. This is three-dimensionally repeated, the arrangement of cations and anions alternatively three-dimensionally in ionic solids. This is a NaCl crystalline solid, and what happened to this solid? The size of anion and cation is same due to some reasons. Suppose Cl minus ion is missed from the lattice point. Cl minus Na plus. Cl minus Na plus. I am sorry, writing some wrong information. Yes. Now observe, dear students. Suppose Cl minus ion is missed from its place, and what happened? Disturbance in electrical neutrality. So here 12, 6 cations and 6 anions are present. 4 4s are 16. 8 cations and 8 anions are present. Now it becomes, due to some reasons, one Cl minus ion is completely missing from the lattice. Then, in order to maintain electrical neutrality, one cation should be wantedly pushed out to maintain neutrality, where anywhere from the crystal, not only here, anywhere from the crystal, here what is missing? One cation. Suppose here one anion is missing and here one cation is missing. So here the number of anions and cations which are missing from the crystal is observed here, and that is observed in ionic solids known as Schottky defect. Schottky defect. This is very similar to vacancy defect in covalent solids. In covalent solids it is called vacancy defect. In ionic solid it is named as Schottky defect. What happened to density? Yes, before density, how do we describe? Yes, here equal number of. Yes, you are going to define in the examination about Schottky defect, equal number of anions and cations completely missed from the lattice, escaped, missed from their lattice points. Such defect is named as, answer is Schottky defect, observed in ionic solids. In those ionic solids, how is the size of anion and cation? So here size of anion and cation is nearly same. In this case, the coordination number is 6. High coordination number is observed by ionic solids. They are ready to exhibit this type of stoichiometric defect due to missing of some particles. Formula of the compound not changed. Still, formula of the compound is NaCl, even though 2 Na plus and 2 Cl minus ions are missed, and that is known as the stoichiometric point defect in ionic solids, known as Schottky defect. What happened to density? Very easy. This leads to decrease in density. It is shown by which type of crystals? Ionic crystals, where the size of anion and cation is nearly same. Such type examples are NaCl, KCl, cesium chloride, etc., and silver bromide. Okay. After that, one more we have to take under this ionic solids. Observe this solid, dear students. This is zinc sulfide, zinc blend structure previously discussed. Zinc blend. As anion is smaller and cation is smaller, anion is larger. This is the first observation, easy to identify by you, which is not exactly given in the book. This is my imagination. And smaller cation, larger anion forms a crystal, and this crystal has some gaps. So these are all gaps known as interstitial voids, and due to some reason smaller cation start dislocating. Smaller cation is dislocating and occupying one of the interstitial voids. So here what is dislocated? Smaller cation is dislocated and it is occupying interstitial void. In this case, the formula of the compound not changed. So this is also a stoichiometric defect, and it is observed in ionic solids, and here a gap is resulted, correct, but dislocation, it is not completely escaped from the student is not completely pushed out from the classroom due to indisciplined activity. He only or she only asked to stand in the classroom like that. The particle here dislocated from this position and occupying interstitial void is known as another point defect under stoichiometric. Point stoichiometric defect is Frankel defect. As the particles are within the sphere, within the lattice, therefore no change in density. Definition is taken. Dislocation of dislocation of smaller cation and occupy interstitial space. Why simply interstitial space, nothing but void. Such defect is known as Frankel defect. Due to this, density is not affected. No change in density. It is performed by ionic solids where the sizes of anion. Ionic solids with different sizes of anion and cation. Example, ZNS and other examples: silver chloride, silver bromide, silver iodide, silver salts. Previously, you will have a doubt. Previously, AgBr is also taken under different conditions. What is the information? AgBr is such an ionic crystal, exhibits based on different conditions, exhibit both Frankel and Schottky defect. It exhibits Frankel as well as Schottky defect. This is a competitive point of view useful, Schottky defect. Name the crystal which exhibits both Frankel and Schottky defects under different conditions, not under the same conditions. Answer is AgBr. This is the information that is sufficient. And here the coordination number. Each zinc ion is surrounded by 4 S2 minus ions. Each S2 minus ion is surrounded by 4 Zn2 plus ions. The coordination number is less in this case, Frankel defect. In NaCl coordination number is 6. So high coordination number ionic salts exhibit Schottky defect. Low coordination number solids exhibit Frankel defect. I hope you followed this one. Will be continue on. Let us have a look at point defects, also known as intrinsic defects or thermodynamic defects, as in covalent solids, as vacancy defect, where the particle is completely missed from the lattice point. 2. Vacancy defect, interstitial defect. Interstitial defect. Yes, information is same but names are different when you are coming to ionic solids. In ionic solids, as equal number of anions and cations missed from their lattice points is a Schottky defect. Correct. Next, smaller cation is dislocated from its lattice point and occupy the space. That is Frankel defect. Frankel defect. Over. That is about this. And other things come to Schottky defect. 1 centimeter volume of 1 centimeter cube volume of NaCl contains 10 to the power 22 ions. NaCl crystal contains 1 centimeter cube volume. Volume of NaCl contains. Now more meaningful. Then in 1 centimeter cube, 10 to the power 6 Schottky defects are observed. Now, Therefore, one Schottky defect is observed for how many ions? This is here substituted, dear students. 10 to the power 6 Schottky defects in 10 to the power 22 ions and one Schottky defect for how many ions? Therefore, answer 10 to the power 22 into 1 by 10 to the power 6. Answer is 10 to the power 16. For competitive point of view, you just refer, dear student. After discussing stoichiometric defects in covalent solids, vacancy and interstitial defects, in ionic solids, Frenkel and Schottky defects, impurity defects, very simple impurity defect. Here what is noticed? NaCl crystal if you take and little amount of strontium chloride is introduced, little amount of with small amounts of strontium chloride. Understand, dear students? Sodium chloride, Na plus Cl minus, Na plus Cl minus alternatively arranged. Okay, right. SrCl2 divided into Sr2 plus and Cl minus ions. Here Sr2 plus ions want to come into the crystal, just like one student is newly joined and want to join in the current class, running class. So Sr2 plus want to come, automatically one ion should be dislocated. Which one? Either Cl minus or Na plus. Here Na plus is removed. Okay, Na plus is completely escaped. In order to accommodate Sr2 plus ions, what is dislocated, what is escaped, what is missed? One Na plus. Then what is introduced here? Sr2 plus is introduced here, but electrical neutrality is failed. Why? Because here 8 cations and 8 anions. Balancing is there, electrical neutrality. Now it becomes 7 plus and 8 minus. In the place of 1 Na plus, what is introduced? 1 Sr2 plus introduced. Now 7 plus becomes 9 plus. What happened? More positive charge is there. That is to be maintained, balanced. How? This 9 plus should be reduced. Not possible to invite one more Cl minus. Here Cl minus ions are available. There is no chance to invite Cl minus ions. Places are not there. Therefore, another one is a vacancy is created by escaping off. Yes. Here what is resulted? A vacancy is resulted due to additional small amounts of higher charge SrCl2 to NaCl. What is the condition? To NaCl we are going to add an impurity with higher charge of cation. Then this is resulted, and what is also produced? Cation vacancy is resulted. Cation vacancy or a vacancy is resulted. Such defect is known as impurity defect. I hope you followed. So therefore, if you introduce 0.5 mole of SrCl2 to 1 mole NaCl, how many moles of vacancies, cation vacancies resulted? Same number. Here 1 Sr2 plus introduced, 1 vacancy resulted. Suppose Al3 plus is introduced. So here 1 Al3 plus, then that becomes previously 8 minus, 8 plus, then that becomes 7 plus and 8 minus in order to invite one Al3 plus ion, then Al3 plus ion after introducing it becomes 10, 10 plus charges and 8 minus. Automatically in order to maintain electrical neutrality, 2 positive ions should be removed. 2 vacancies are resulted by introducing 1 Al3 plus. 1 Sr2 plus if you introduce 1 vacancy of cation is resulted. I hope you followed about this impurity defect.